Hi, my name is Evan Custodio, and this is Haptyc, a library for building microfuzzers in Turbo Intruder, or a fuzzing framework for Turbo Intruder. So back in March, I saw a tweet from Nafi that looked like this. It just showed an image of normal Intruder with a cluster bomb style of attack with position payloads on both the method and the path. And this is typical if you want to brute force admin panel endpoints, mutating it in different ways, while also for each mutation testing a different HTTP method type. And I thought, well, I don't really use Intruder anymore. I kind of moved my workloads all the way to Turbo Intruder. What would this look like in Turbo Intruder? So a day later, I wrote up about 100 line Python gist that did the exact same thing and accomplished the exact same goal. But there was a couple of problems with this implementation. One, the entire HTTP request is sort of hard coded into the Python because there isn't really a way to use the original HTTP payload that's given into Turbo Intruder, and still keeping insertion tags or payload insertion tags. And so that got me sort of feeling unsatisfied and wanted to figure out, well, how do I add that type of functionality into Turbo Intruder? How do we add multiple payload insertion points, but also be able to specify attacks, not just sniper attacks, but also cluster bomb style and battering ram style attacks into Turbo Intruder. And so I went on the path to building a library for Turbo Intruder called Haptyc. And so Haptyc is a Python library um, which gets embedded right into Turbo Intruder jar file. It's not a burp plugin at all. And really the way you enable it in your Turbo Intruder Python is basically to first line import it just like this from Haptic import, star. And so it's easy as that to enable it. And the goals for this library, one, are to get the same exact supported payload markers that we have in traditional Intruder, but also to enable Turbo Intruder to have the same type of attack types that are in traditional Intruder, like sniper, cluster bomb, battering ram. Um, and so I went off and I built this library, and as I was testing it to completion, I noticed some positive side effects from the library. First being, it significantly reduced the Python code size and trade for actual readable Python. It also created these portable fuzzers and testers. The Python that you'd write can actually be reused across um, HTTP types from the repeater. So you could send anything from the repeater and reuse sort of the same types of fuzzers that you've built. And also enabled easy structure aware fuzzing, and I'll explain what that is later in the presentation. So here's a basic example. This is a full example, about 20 lines of code. Um, there's nothing more to it than really just this. Um, First, we enable the library by importing Haptic by doing from Haptic import star. And this will import all the different Haptic related classes, decorators, class decorators, and helper functions. The first thing you need to do is create a class. You can call it whatever you want. In this case, I call it test logic, but it must extend the transform class from Haptic. The transform class is what adds the nuts and bolts into your Haptic class. And inside your Haptic class, you specify sort of test names, and they all must start with test underscore. Whatever the name you want after the underscore is up to you, and whatever you do name it, it will translate into these tags right here. And so in this case, I have test underscore h1, and if you notice in front of the method, I have what I call a logic decorator. It places logic, state logic into the test. And this specific one, this is probably the most popular one that I use. It's apply iteration 5. And what this tells the method is that if you find the h1 tag in the HTTP request create 5 test cases returning moose in its place, right? So, so that's basically what that says. So if we look at the rest of the Python, it's normal Turbo Intruder boilerplate Python. We have the queue requests function, and we have the handle response function. And so when you first click attack, the queue request function is executed. It builds a request engine. And then with that request engine, you need to issue out the tests. So to do that with Haptyc, um, you basically take the class that you created with Haptyc, in this case it's test logic, and you instantiate an object. The during instantiation, in the constructor receives the actual HTTP payload string with all the Haptyc annotations. And so with that, it creates an object. In this case, we call it test factory because it acts sort of like a test factory. And um, on the next in the next step, there's a loop here that sort of asks the question of, hey, or starts the question of, hey, for every test in test factory, could you please create a test for me? Figure out all the tests, please, and let's go ahead and queue them into the engine. And so what happens here specifically with this test called H1, if you if you look at if you look at the get being this get request sort of being your initial HTTP payload, you're going to be annotating it with this H1 tag around your payload of interest. And so what this sort of um, Haptyc transform does is it replaces that entire tag plus what's inside the inner part of that tag with the literal moose shown there, and it does it for 5 tests, and that's exactly sort of what this snippet does. And this type of test, as simple as it looks right now, this type of framework is extremely powerful for fuzzing different types of payloads into different areas of your HTTP requests. And in sort of the next few moments, I'll go through different demos of how we do that. So here we have Turbo Intruder open with the Python shown from the previous slide. And in this Python, we have our test logic class with our test h1 tag. And so the way we apply this tag is we simply just go ahead and do plus h1 plus end. And then we can surround these tags anywhere in the payload. So for instance, I'm going to be targeting this car payload right here. And what this should do when we click attack is this will evaluate this test for 5 times as shown in apply iteration state logic, and it should return moose in place of car. So if we do that, and then we see that indeed type equals moose. Now if we go ahead and we just return data, data is given to h1 through the tag. So anything that's inside the tag will be placed into the h1 routine as data. So we can just return data back. If we do that, it shows that we now have car and replace the whole transform with car. We can go ahead and we can make this iteration number count anything we want. We can make it 5, we can make it 10, and it will go ahead and scale with that number. So now next what we're going to do is we're going to show how we can sort of surround the data with different things. So for instance, because this is an iterative transform, the state variable keeps track of which of the iteration count that this transform has. So if we do say string state dot iter and we append it to the data and attack, we'll see that we get car 0, car 1, 4, 5, 6, 7, 8, 9. So this is being able to take the data in through the tag and be able to manipulate it and return it back is a strong property of Haptyc, and what makes it so powerful. So next, one of the things we can do is you can pretty much add whatever amount you want for this iteration. So let's say we're asking for 1,000,000 requests, but let's say we don't want to do 1,000,000 requests. We want to stop at some number. So we can do something like this where we go if state dot iter is greater than equal to say 15, we can tell it to just stop right here. And it won't go to 1,000,000 requests. Instead, it will stop right at the 15th request. So using the stop function is a good way to basically bail out of a test series when some condition has been met. So next we'll take a look at some helper functions that we can use to mutate the data. So one of the helper functions that we have is Radomza. So as long as you've installed Radomza, if you're running burp in Linux and Radomza is installed in your path, or if you're running burp in Windows and Radomza is installed in your WSL, it should work either way. I have not tested this on OS X. I'm not a big OS X fan, but it should work in OS X too. If not, let me know. So you can apply Radomza and it will mutate this. In fact, let's just go ahead and show how we can just move the tag around and to mutate something else. So we'll leave car alone. We'll go to the user agent and we'll try to mutate that for 10 tests. And we see here, as we move forward, Radomza is mutating the user agent. Another thing we can do, another helper function that we have is the helper function is called random insert and index insert. So we'll show random insert first. Random insert takes the data as the first argument. The next argument, it takes a list of different insert strings. So right now I'll just show one. So let's say we want to insert ticks randomly inside of data. So what this will do is wherever we place this tag, let's place it at the host. So we're on the host now. It will randomly find a spot in this data tag and it will insert a random character that's in this list. Right now there's only one character, so it'll just put ticks in. So let's take a look at that. And then you see as I go down the list, it randomly places ticks. We can also do a index insert, which allows you to control the index. So let's say we don't want to randomly place ticks everywhere. Instead, we want to actually walk the tick from the beginning to the end of the data string. So what we can do is we can use actually state.iter to get the iteration count, because that should go from 0 to your iteration max. And we can put a high iteration max of say 1,000. What index insert will do is if your iteration count goes past the length of data that's inside of the tag, it will automatically bail out of the tag. So this won't go to 1,000. So let's take a look at that. Say it stops right at the 18th. And if we take a look at that, we see that the tick is walking across the host name, just like that. Another property of this is not just, you could use multiple types of characters to insert or strings to insert. So let's say we want to insert 0A% and maybe 0D. And what will happen is as it walks across the entire string, it will randomly choose which one of these three to insert. So we see that again. We see that it's randomly choosing tick 0D and 0A. So far, we've only shown you the apply iteration logic decorator for our transforms. There are 4 other decorator types that can be used with Haptyc that may be useful. The first one shown here is called apply range, and this works just like the Python range function, where you give a starting value, your end value, and your step. And your step can also be fractional, so you can go up in steps of say 0.1. And what happens is for every value that's produced, it will invoke a test with that value placed inside for data. If you want the original data that's inside of the tag for this specific test, you can use self.inner at any time to get the original inner data and mutate it along with the range values that you're getting. Apply list works the same way, except for numbers. You supply a Python list just like this, and each element of that list creates a test and is placed into data. Same with file list, except with file list, it opens up a file, splits each line into an element, and then each element is placed into the transform as a data value. Apply payloads is is a decorator that basically grabs a pre-packaged payload file that's packaged with Haptyc. In this case, we have a whole bunch of payload files that were gathered from Burp. Specifically here, we grab a payload file I put here. That's the word list from dir search. And for every word inside of the dir search word list gets supplied into H5 as data. And then we can replace the extension identifier with whatever extension you want, and that gets placed into H5. And so previously we've shown the plus sign style attack. So with the plus sign style attack, that's a sniper attack. And so with sniper, it just goes through the payload lists one at a time. So in this case, we have two H2 tags here, which is fine for the plus sign style attack. You can have multiple of these H2s called out. And what will happen is the ID, the H2 tag at the ID will get evaluated first with any placed as the value inside of type. And then null gets placed inside of ID, and then this H2 tag gets evaluated. And so since H2 is 5 tests, we should have a total of 10 tests here, which we do. And we see this goes from 0 to 4, and this goes from 0 to 4 on the other parameter. If we wanted to do a cluster bomb style of attack, instead of the plus sign, we use a percent sign. And so we'll put a percent sign here, put a percent sign here, and you cannot use the same haptic transform. You have to use a different one because each transform keeps its own state and they're both being used at the same time. So in this case, we're going to use H2 and H3. And so for every test value in H2, it will go through every value of H3. And so that would be 5 tests multiplied by 5 tests. So it should be 25 tests in total. And there are. And you see as we go up from 0 to 5, 0 to 4, it goes through each value inside of the H3 tag. And then the last attack type is the battering ram / pitchfork style, which is the number sign, noted by the number sign here. And so what this does is it evaluates each of the tags and places their value in parallel. So in this case, this is more pitchfork style because there are different payload sets being placed into their positions. So we go ahead, should be only 5 tests, but you see they have their individual tags evaluated and placed into the position. One of the things you might notice is that as I was testing that this user agent's being mutated, that is another style of tag called a persistent transform. With persistent transforms, they're denoted by PER underscore to start the method, and you can place them anywhere. They contain no state and they prescribe no tests, so they only get evaluated with other tests, and they always get evaluated independent of those tests. So this is a good way to sort of just, if you need to compute a hash or just perform just naive manipulation, you can sort of add these persistent transforms, and they don't affect the state at all of the iterative transforms. Lastly, this clone transform is used for creating battering ram style attacks. So this attack right here is a pitchfork style because it's using 2 different payload sets. But how do we use the same payload set when you can't use the same tag twice? So what we do here is we use clone transform to copy or just basically clone H3 into H3C. And now it'll use the same exact payload set. So we can go ahead and change this to H3C, and we have 5 tests, but we can see they're using a battering ram style attack to use with the same exact payload for each position. So let's now go into a couple of advanced use cases for fuzzing with Haptyc. In this case, we see 2 fields. One is a cookie message field that looks base 64 encoded, and we have a JSON structure with 4 keys, which its payloads also look base 64 encoded. Now, if you were to just place Radomza or random insert at these values at this level, chances are you'd either be getting errors back from the base64 decoder or the JSON deserializer at the application, and you wouldn't get very far in the logic path. What we can do with Haptyc is we can create transforms that understand the structure of the message we are fuzzing and try to get a layer deeper. So in the case of this cookie, we see that it's base64 encoded, so we'll instead decode it, fuzz at that level, and then re-encode it. And in the case of this JSON structure, we see that we probably want to fuzz the values that are inside of these base64 encoded keys. So first we have to deserialize the JSON structure, access all the keys, and decode the base64, fuzz at that level, re-encode the base64, and serialize the JSON structure. And so we can do that in pretty small amounts of code here with 2 tags. The H1 tag takes the data, decodes it, performs a random insert, and then re-encodes it and sends it into the application. And in the case with JSON fuzz, it loads the data into a JSON deserializer. For every key found in that JSON structure, it will decode the value in that key, randomly insert a character from this list, and then re-encode it back into that key location, and then re-encode the entire JSON structure and send it back in. So and both tags are now placed in the payload as a pitchfork style, so they'll both execute in parallel. So let's see what we get. So we get 50 different tests. We see they're mostly 51 words, except there's a couple that's 56. So if we take a look, we see indeed that all the base64 values are getting manipulated. And we also see that the message is getting that insertion from the H1 tag, random insert of a tick. When we go down to that message that's 56 bytes, or 56 words, we see that we triggered an error at the key in the JSON structure labeled D, that carets aren't allowed in the D parameter. And so this is a good way to what's called structured aware fuzzing, where we understand the structure at 1 level deep or 2 level deep and create a transform to fuzz at those deep levels. So now that you know a little bit about Haptyc, let's go back to NAFI's original example and my response to it. So the response to it was about 100 lines of Python code written for Turbo Intruder that was pretty much unreadable, or at least very difficult to handle. Here we've reduced it, the same exact type of function, down to 20 lines of Python code using Haptyc. We have basically created position tags called method and path that associate to these 2 transform functions. In this first transform function, we iterate through get, post, put, and patch for every payload that's found in the admin's prepackaged word list. So this would be, number of tests will be 4 times the number of entries in this word list. And so we put the method here and put the path there. And so if we go ahead and issue out the attack, we see that some of the stuff is hitting. Let's now use a what's called a response decorator that's been added to Turbo Intruder to dedupe some of the responses. So go ahead and add unique size 1. And this should dedupe all common responses and leave only ones that appear different. So here we go. We have 404 not found. We have a 405 method not allowed, showing that there are some allowed methods, options, and put. and then we have it shows here that we found the admin panel using the put method at /admin/. So that's it. Thank you for watching this presentation on Haptyc. Thank you to all my friends at HactivityCon for inviting me here to give this talk. Everyone can now go ahead and clone Haptyc. It's here on GitHub on this link shown here. Um, Feel free to look through the examples folder. I know a lot of the concepts I showed here today are pretty advanced, but I feel like if you check out the examples and try to run through them, you'll intuitively get sort of the look and feel of how to use the library. If you haven't already, follow me on Twitter at defparem, and that's it. Thank you, everyone.